All right, let's dive deep into the world of bare metal programming. We're going to answer a question that's actually pretty fundamental. What really happens before your main function ever gets called? We're going to trace that journey, right, from the first jolt of electricity all the way to the first line of code you actually wrote. Let's get into it.
So, we all know main, right? It's the heart of our C programs. On your laptop, it's simple. The operating system kicks things off. But what about on a bare microcontroller, a blank chip with no OS, no safety net? Who or what makes that first call? Well, that's the big mystery we're solving today. First things first, we need to set the scene. I want you to imagine a world with no Windows, no Linux, no Mac OS. There's nothing. There is no safety net. And that world has a name. Bare metal programming. It means your software, your firmware, is running directly on the hardware itself. It's the very first code to run when the chip wakes up, and it stays in complete control until you pull the plug. You are, quite literally, the king of the castle. And believe me, the difference in responsibility here is just huge. Writing a desktop app is kind of like moving into a fully furnished apartment. You know, the lights work, the water runs, the OS handles all of that. But bare metal? You're given a plot of land and a pile of bricks. You have to pour the foundation, put up the walls, run the electrical. You have to build everything from scratch. So what's on that plot of land? What are these building materials we get to work with? Well, a modern microcontroller is basically a whole system on a chip. It's got all the essential hardware packed right in there. For what we're talking about today, the two most important parts are the two kinds of memory. First up, you've got flash memory. This stuff is non-volatile, which means it remembers everything, even with the power off. It's the permanent home for our program code. Then you have SRAM. This is our volatile memory, our scratch pad. It's a temporary workspace for all our variables and data while the program is running. The second the power goes out, poof, everything in SRAM is gone. Okay, so we've got our hardware, we know about our memory. Now, how do we actually forge the code to run on it? It's not as simple as hitting compile on a desktop app. We need a pretty special process. This is our toolchain. You can think of it like an assembly line that turns our human-readable C code into raw machine code that the chip can understand. It starts with pre-processing, then compilation, then assembly, and finally, the most important step for our story today, linking, which pieces everything together into one program. And at the very end of that assembly line, we get a few key files. The one we really care about is the .bin or .hex file. Now, this is not a program you can run on your computer. It is the raw binary image, just a pure sequence of ones and zeros that we are going to flash or write directly onto the microcontroller's flash memory. But hang on a second. How does the toolchain know where to put all those ones and zeros? I mean, where in the memory do they go? For that, we need a blueprint. And this blueprint is called the linker script. This is one of the most critical and, honestly, most overlooked files in bare metal development. If our chip is that plot of land, the linker script is the detailed architectural plan that tells our builder, the linker, exactly where every single function, every variable, every little piece of code is supposed to go. And here's basically how that plan works. The linker organizes our program into different sections. Our actual executable code, the .text section, that goes into the permanent flash memory. But our variables, which are in sections called .data and .bss, they need to live in that read-write SRAM. And the key thing here is that the linker script makes a plan for how they're going to get set up in SRAM right when the chip starts up. Okay, this is it. This is the moment we've been building towards. All the pieces are in place. The hardware is ready. Our code is compiled and sitting in flash memory, all laid out according to our blueprint. It's time to flip the switch, power on the device, and finally trace that journey to main. The instant power hits that chip, a sequence that's totally controlled by the hardware unfolds. It's incredibly fast. The CPU resets, then it immediately does two things. It loads an address into something called the stack pointer. Just think of it as a bookmark for now. And then it loads another address into the program counter, which is the thing that always points to the next instruction to run. And that address is our entry point, the reset handler. So, what is this reset handler? Did you write it? Nope. It's a small, clever piece of assembly code that's usually provided by the chip manufacturer. We call it the startup code, and you can think of it like the construction site foreman. It's the very first code to show up, and its only job is to get everything ready before the real work, your main function, can even begin. And right here, this is the answer to our question. The startup code has a very precise checklist. First, it goes to Flash and copies the initial values for your global variables, that .data section, over to their working home in SRAM. Second, it clears out the memory for all your uninitialized variables, the .bs section, and only when the memory is absolutely perfect, only then does it make one final call to your main function. So the big takeaway is this: main is never the first thing to run.
So, we finally made it. We've arrived at main function. But what happens now is totally different from what you'd see in a desktop program.
See, a desktop app runs, it does its job, and then it exits. It hands control back to the operating system. But in our world, on a bare metal device, there is no operating system to return to. Your program is the entire system. So the standard way to handle this is to enter an infinite loop, what we often call a super loop. That program will run forever, executing the code inside that loop over and over until you cut the power.
And there you have it. That is the entire life cycle of a bare metal program, from start to finish. It goes from the hardware reset at power on, to the startup code getting all the memory ready, to that first call to your main function, and then finally into the infinite loop where it's going to live out the rest of its days.
So that's the journey. But this leaves us with a really important question, doesn't it? If our code is just spinning and spinning in this endless loop, how can it possibly react instantly to something happening in the real world, like a button press? How does it handle important events without missing a beat? Well, the answer to that lies in the incredible power of interrupts, but that's a story for our next explainer.